So good morning, Sergio, or good afternoon. We're very glad to have you with us, and your wing person will be Audi. And so I'm gonna just stop talking and let you go ahead. You're gonna talk about tweaking ECP performance and in libRIST. So guys, take it away, and we're really glad to have you. Thank you so much for presenting.
Yes, thank you for being our opening speakers.
My name is Sergio Ammirata, and today I will be talking to you about tweaking ECP performance on libRIST. Before we begin, let me put things into context, right? First of all, what do we mean by ECP? In this context, ECP stands for Error Correction Protocol. Particularly, we will be covering aspects of the RIST protocol itself. Okay. Now, the other two things that I'm going to bring next is a brief introduction to SipRadius and to libRIST itself. SipRadius is a technology company that specializes on Linux appliance solutions. We are the creators and maintainers of Core Linux, a mature 20-year-old Linux distro that is focused on efficiency and security. We have 11 years of experience creating transport products for the broadcast industry on top of this Linux platform. And we are the creators of the patented error correction protocol, commonly known as Dozer.
So, Sergio,
go ahead.
How are you doing? Good morning.
Good morning.
Can you elaborate on libRIST?
Absolutely.
Why should I use that?
Okay, here, let me go. Oh. There you go. Excellent. So what is libRIST, right? libRIST is a free and open source library. It comes with over 7 years of know-how that were pumped into it from the Dozer technology, and it's been public for about a year. It's a public open source project. It's free to use, and it's production ready today. So libRIST is the library that allows you to implement the RIST protocol in your own application, in your own appliance. So what will we be discussing today? We will be basically do a brief overview of the major features of the library that make it special. And then we will go into some of the detail of the items and a small demo as well. So let's talk about the history of libRIST a little bit. Like I was saying, a year ago, we published this library. We made it open source. And then, in 1 year, it has had 675 commits. Commit to a public repository is, official pushes to the repository. It's hosted in the VideoLAN GitLab, and it's a very active project. The code is solid, mature, and compilable on pretty much every architecture and operating system. It performs equal or better than most commercial protocols and solutions out there. And we just released a new version, 0.2.0, which is now being, as we speak, merged into both VLC 4.0 and NFFmpeg 4.3.
So hold on, wait a second. You're talking about RIST. What RIST protocol? What RIST specification do you support?
Currently, the libRIST library supports the basic, the simple profile, and the main profile, both. It supports PSK, but it does not support DTLS for encryption.
Okay. Any other enhancements that you added?
Well, it has support for multipath, redundancy. It supports real-time buffering, so you can synchronize multiple streams. There's a new version that is coming with a tunneling support as well for all the other data types.
Excellent.
I'm not going to go into a lot of detail of all the features that it has. It would be a full presentation on that. In this presentation, I'm going to focus mostly on the congestion control, what makes it so unique. And you'll see why in a second. So let's go to the reaching more platforms, right? In the past, we've seen how easy it is to build the libRIST library on Linux desktops, right? It's, we have another full presentation on this. Now, we've enhanced it so that we support compilation in Visual Studio directly for people that work on Windows. Also, we've enhanced support for many different architectures and platforms. This particular screenshot is for the library being compiled on AWS new ARM machines. If you want to see more on how libRIST can be used, you can visit the SipRadius booth, and we have a full-blown multi-platform demo. This is just a diagram of that particular demo. We have an NDI conversion to an MPEG-TS H.264. We send it to a Raspberry Pi running regular, Raspbian with libRIST on it. Then we push that with libRIST to an AWS machine running SipRadius OS. From there, we push it again to an Azure machine running Ubuntu on libRIST, and then we'll push it again to a machine in Texas running VMware and receiving it with libRIST, and then converting it out to WebRTC and to NDI again. So this is the demo that shows the potential capabilities that you have with the library and with the RIST protocol itself. Just an idea of what you can do.
So where can we see this demo?
That's on the SipRadius booth.
Is that running on your booth?
The booth
okay.
The booth
I understand that.
The source video, and then we'll show you the rest there. So let's talk about performance gains now. Okay, congestion controls, right? ECP solutions have been around for a long time, well before RIST was created. There are many proprietary versions of ECP, and please don't get offended if the company is not up there. There are also many different implementations of the RIST protocol itself done by quite a few companies. And in reality, all of them work well under ideal network conditions. What are ideal conditions? Maybe 10% of less of random packet loss, and no bandwidth limitations of any kind, right? So that you can, send bursts of data to recover the host. Under those conditions, any solution out there will probably perform very similarly.
Okay, go on.
Now, what happens? What happens when the network is not so well behaved, right?
Right.
What happens when our total bandwidth is barely above the transmission bit rate? Now, this is where the different solutions and implementations diverge, and this is where libRIST shines. I'm not saying that other implementations might not have similar characteristics, but we've gone a great deal into making it work on their adverse network conditions. Next slide.
Basically, you say prepare for the worst.
Correct.
That is, you never know what will happen whenever Facebook will crash or somebody else. You have to be prepared. Correct. That is the purpose of this presentation, congestion control. Be ready to outperform and get your feed 24/7 or without any packet loss. Right. That's what
the perfect example is this conference, the conference itself. We are now experiencing worst case conditions with congestion, the site, and this and that. You need to prepare for that, because preparing for just when everything is smooth is not good enough. So what have we done inside libRIST? So first, we protect the link itself by having a built-in self-managing of the max bandwidth used by the sender. So if you have a link that is of a particular size, the protocol itself, or the implementation of the protocol, is going to make sure that you don't exceed that bandwidth. Then we've also accurately and repeatedly measured the round trip time. We do 10 times per second, and then use that round trip time inside our algorithm to space our retries. And why is that important? Because that's the time it takes for a communication to go back and forth. Third, when a burst of packet loss is encountered, which are very common, high packet loss, over a small period of time, the library actually spreads the retries over time to prevent and avoid network collapse. And lastly, now that we have a queue managing these retries, we don't resend for expired packets or queue retry requests, which are already in the retry queue. If we have a misbehaving peer on the other side sending too many retries, it doesn't affect or doesn't collapse the network, because our library takes care of properly enforcing certain set of rules. So what are the benefits?
Just understand from, hold on, just to understand. This is on the sender side, right? The sender is the smart, so
Correct.
the sender is the one controlling the everything, getting the responses, tweaking and controlling the retransmission, the retrials, and it can control the congestion. So it is in control, steering the streaming to the destination, and uses whatever the RIST protocol and specification allowing to do. I assume that you use the RTT echo feature from the simple profile, and then you use a smart throttling that is allowed in the simple profile and in the main profile of the RIST protocol.
That is correct, yes. Of course, there's also code on the other side, so making sure that the receiver spaces the retries by the proper amount, but the congestion control itself is done by the sender, which is the one that controls the data going out. So what are the benefits of all these measures we've taken within the library? Well, by measuring and using the RTT in real time, we can minimize the number of redundant messages sent from the client to the receiver. So this means that we are as efficient as possible, thus leaving room for recovery at higher loss rates. And third, by controlling the max bandwidth, we prevent a link collapse, which is very common with a lot of the existing solutions out there.
For those who are asking a question about the RTT, because it's a vital part, why to use the RTT measurement from the RIST and not simple ping? What's the benefit there?
The difference is when you do a ping on people are very used to a ping command on Windows. You type ping and you're done. That uses the IGMP protocol. It's a totally different way of sending data. It traverses routers differently, and it's going to give you an invalid response. A lot of the time, the ping response doesn't even come from the end machine. It can come from an added device, an added router. We use the echo packet inside the RIST protocol, which gives you the equivalent of a ping, but through the same UDP path back and forth that you have where your data is going through. So it's the ideal and accurate way of measuring the round trip time for your transmission packets. That's why it's so important to use that as the measurement and not a normal ping. And it's also important to measure in real time and continuously refresh that. We do it 10 times a second, and we keep an instant average and a rolling average of the values and the user within our protocol. So basically the result of fixing the bugs and adding all these features was that now we can recover from continuous packet loss. It used to be 50%, now it's 70% what we can do with the library, continuous packet loss, and recover every single data packet on it. Let's go to the next one. So let's summarize the tweaks again that are related to congestion control. There's a lot of other features that we can talk about, but this is only congestion control. We have implemented congestion control in the sender using real-time RTT measurement and retry queue management, instead of relying on information passed to us from the receiver. There's some data in the RTCP packets that has to do with the bandwidth and other things. We ignore all that, and in the library, we use just algorithms based on the data on the retries received. So this makes the library very resilient. Even when connected to a less featured peer on the other side, the receiver can be non-compliant. It can be trying to flood us with excessive retries or not spaced properly. If you have libRIST on the sender, your link is protected. All right, so now let's talk about the demo / stress test. What we're basically going to show briefly is, what we've done here. We have a device, that is the network emulator device. Okay, for the demo, we have created, we needed a product that did a link emulation, without a lot of bells and whistles. There's companies out there that create this type of products, PacketStorm and others, that have a lot of features. We needed something simple that we could just create a link and simulate packet loss, packet corruption, packet duplication, and packet reordering. at a global level. No filtering, no IPs, everything that goes through it. So we created our own version of such solution, which is what we're going to show. This is basically it acts like a switch, and we connect two machines together to two ports and feed it to this. And this is going to simulate an internet connection, and we're going to be able to go ahead and change the settings as we see fit. So now we're going to switch to the demo and show you the menus of the sender, the packet emulator, the receiver, and show you the video playback.
So can you just describe the demo scenario? It's a benchtop field test.
If you go to our booth eventually, the video camera that points here where we're at, you would see the three machines right here in front of me. It's the three machines. One generates a stream. One is the network emulator. The other one receives the stream. And the one that receives the streams is sending it to my laptop, and I'm playing it on VLC. And switch to, this is the video that I'm receiving on my laptop from that demo. It's just, I guess, the landings of the new Mars rover. And I'm going to show you now briefly, the configuration of the machines. What we're basically doing here, it's pretty simple. We're grabbing a file, the NASA Perseverance is sent file, an MP4. We're pushing it as IP UDP stream on a local host. Then on that same machine, we're grabbing and creating a RIST tunnel. The RIST is receiving. These are all features of the libRIST, by the way. What we've done is we put a GUI on top of it that makes it easy to use. Okay, so the ECP setup is where the RIST goes. And we basically grab that UDP streams on port 1111. We encapsulate it in RIST, and then we send it to a remote destination, which is the other machine that I'm going to open now, over a particular port. And for you, those of you that are familiar with the RIST, you can see this is the sender logs, and it gives you detailed statistics once per second of what's happening with the transmission. Then now I'm going to switch to the receiver machine. Well, before that, let me switch to the emulator. The emulator is pretty simple. You saw that it's a multi-port device. For each port, we can go ahead and configure these basic parameters and apply the settings, changing the settings. We configure the max bandwidth, the delay, the loss, duplication percentage, reordering, etc. So we have it on port 4 and port 5, which are bridged together. That is what is showing right now. And then lastly, on the receive side, we have the ECP setup. This is the receiver service. It's listening to the same port, 8194. And then after that, we push out UDP, the transmission, to a local adapter. And from the local adapter, I have another service pushing it to my machine, where I'm playing it using VLC. And this is the result of that test. So according to my time, we only have about a minute left. And then I wanted to leave a little bit of room for questions. But basically, that's the gist of it. And with this setup, we're able to go ahead and just arbitrarily change this from 20 to 30 to 50 to 70. But the key is when you look at the receive side, and I'm going to show you the logs on the receive side, and I've done this in real-time demos before, this is the relevant information. The library is going to spit out once per second a total cumulative packet loss. It shows you the number of recovered packets and the number of logs since the beginning of the service. It also shows instantaneous, for the last second, a lot of very useful statistics. The packets recovered, they received. Let me zoom this in so you can see more. The last second, quality 91.7%. We received 223. We dropped 0. We recovered 21, etc. So this gives you an idea of the test setup. Very simple, but the whole point was to show that we can go here to 70% and still recover without major issues. Now, I'd like to go back to the presentation and leave some room for questions. So in summary, you have a library that compiles and runs
Reports.
everywhere. It's far superior to many commercial applications, open source solution. Thank you.
Very good. Thank you, Sergio. We really appreciate it. And I had two notes there. One is that Wes had put a note in that the refresh rate was coming from your Zoom channel, not from the RIST demo. So people would see
Correct.
regular frame rates, right?
You're correct. We were playing back the video through the Zoom. That's why it was coming the way it was.
There was a question in the chat about, in terms of performance, how does RIST compare with TCP BBR? Kieran did give an answer, and he said TCP BBR is designed for fairness on the network. RIST is designed to get your content out there, often by more than one ISP. I don't know if you guys had any other comments on that, but that's what Kieran had said. And thank you, Kieran, for picking that up.
Right, that pretty much covers it. I'm good with that answer.
Okay.